del Pezzo surfaces. Okay. Uh, about del Pezzo surfaces, which I'm going to generalize. We see the Pezzo surface for me is a smooth projective surface with simple anti-canonical class. Uh, there are two things we can discuss in this relation. First, projective models. I recall that according to the degree, this is self-intersection number of canonical class. Mm, there are the following cases. For degree 1, the Pezzo surface is embedded to weighted projective space as hypersurface of degree 6, and weights are 1, 1 to 3. For degree 2, this is double curve of P2. On the other hand, it is hypersurface of degree 4 in P1, 1, 1, 2. Degree 3 is a cubic surface, well known. Degree 4 is intersection of two quadrics. Del Pezzo degree 5 is unique up to isomorphism. It's linear section of Grassmannian up to 5. Del Pezzo degree 6 can be realized as a divisor of 3 degree 1, 1, 1 in P1 cross P1 cross P1. Degree 6 is blow up of a point on P2, and degree 8 is either P1 cross P1 or Hirsebruch surface F1, and finally degree 9 is P2. Okay, another approach is to classification is birational one, and we can look this as a blow up of P2. So any del Pezzo surface is either P1 cross P1 or can be realized as blow up of 9 minus degree points in general position on P2. Basic invariant related to the del Pezzo surface is lattice, Picard lattice. This is lattice of rank 10 minus degree and equipped with symmetric bilinear form signature 1 and other, and it's equipped with distinguished element anti-canonical class. Very helpful thing here is that we have root system. If you look at the in orthogonal complement to the canonical class, if you look at the vectors of length minus 2, then they form a root system, and it's of type A. E8, E7, E6, D5, A4, A2 cross A1, and A1, respectively, with respect to the degree. Okay. So I am going to consider a high-dimensional analog, and the definition basically is due to, I think, Takao Fujita, and he proposed the following definition. The Pezzo variety is a Fano variety, possibly singular, Gorenstein, such that anti-canonical class is divisible by dimension -1. Today, I'll consider only Del Pezzo varieties with terminal singularities. Then this line bundle A is uniquely determined. Sometimes it's called the fundamental divisor. So there are standard invariants. This is degree. top self-intersection of this fundamental class. And as in the surface case, we have lattice, but here we consider lattice not Picard lattice, but lattice of well-divided class group. Since we don't assume that our variety is q-factorial, so this is there is some difference. And anyway, this lattice equipped with natural symmetric bilinear form, defined as follows. Is well defined, and of course we have distinguished element A. This is fundamental divisor, and this pairing AA equals to the degree. And one of the basic invariants we will consider today is rank. This rank of this lattice. Okay, what's good with this form? The good point is that this form is preserved under flops. This is somehow divisorial construction. So once we have a small modification of our variety, it is a composition of flops, and this form is preserved. Okay. So first, of course, I want to discuss projective models. And this is due to many people, maybe starting with Skorsky, Fujita, and many people wrote something. By induction, we can prove that projective classification is the same as for surfaces. So assume that we have del Pezzo variety of dimension at least 3 now. Then its degree is between 1 and 8, and you have the same projective the same projective models. If degree is 1, then it is weighted hypersurface of degree 6. In this projective space. In degree 2, this is again weighted projective hypersurface of degree 4. Degree 3, it's a cubic. Degree 4, it is an intersection of two quadrics. In degree 5, this is linear section of Grassmannian. Actually, for smooth varieties, it was known, but for singular case, we couldn't find the reference, so we proved it again. In degree 6, we have two possibilities. This is either linear section of P2 cross P2 embedded by Segre, or P1 cross P1 cross P1. Degree 7, this is blow up of P3, and in degree 8 we have just one possibility. This is P3. I just want to say that we assume that X is not a cone. To exclude again for today talk, I assume that it's not a cone of a low dimensional variety. To exclude trivial case, of course, in higher dimension we can take cone over some of this variety, and we get more we get variety of higher dimension. Okay, so this is not difficult to obtain, but actually it's not satisfactory since we don't know many things about singularities and birational geometry. I am going to discuss birational geometry. At this point, it's convenient to consider almost del Pezzo variety. Again, for today, this variety with terminal Gorenstein singularities, such that anti-canonical class is divisible by dimension -1. And this primitive element is nef and big, this is Cartier represented by Cartier divisor. And we claim that morphism given by multiple linear system doesn't contract any divisors. Maybe I should recall that small Q factorization of a variety is a projective birational morphism x hat to x, such that x hat has only Q factorial, is Q factorial, and this map doesn't contract divisors. Actually, by MMP, we know that if X has only commutative terminal singularities, in particular if it's terminal, then co-factorization exists, but it's not unique. Any two co-factorizations differs by flops, composition of flops. So we can define Crepin model of X, Fx of almost del Pezzo variety is a variety such that we have isomorphism. This is isomorphism in codimension 1. Just as a corollary, we know that if we have del Pezzo variety, then its co-factorization is a almost del Pezzo variety. And conversely, if we have almost del Pezzo variety, then its anti-canonical model is the del Pezzo. Okay, now I want to run MMP on del Pezzo varieties. And the following fact, this is not difficult and can be proved by induction. Suppose we have del Pezzo variety, which is Q factorial, almost del Pezzo, of dimension n, and suppose we have Mori contraction. So this extremal construction, which is k negative, then we have one of the following. If this contraction is birational, then the target variety is Q factorial, almost del Pezzo. And this map is just inverse to the blow up of a smooth point. So this step is very easy. This is because, of course, canonical class is divisible, is very divisible. Another thing, if we have Mori fiber space, again, we have not so many possibilities. If either that is a surface, then this is a smooth del Pezzo surface, and our map is just a Pn-1 n-2 bundle. In particular, X is smooth in this case. If the target is a curve, then F is just quadratic bundle. And finally, it's possible that the target is a point, and then rank of original variety is just 1. As a corollary, we have that in the category of Q factorial almost del Pezzo varieties, we can run DMMP with respect to any divisor. This means that we can contract extremal rays and make flips with respect to D, which is D negative. And any step of this MMP is either flop, usual flop, or inverse to the blow up of a smooth point. Basically, important thing that we stay running this procedure, we stay in the category of factorial almost delpetzes. So, just to run, what do we have? If we start with delpetze, then we can it can have maybe several co-factorizations. It's easy to show that there are only finite number of them. And then on each co-factorization we can run MMP as explained, and we get Mori fiber space. Basically, this is analog of blow up model of delpetze surfaces. And definition, we say that some delpetze variety is imprimitive if some co-factorization admits birational Mori contraction. So like here, so we have here on this step is not an isomorphism. Otherwise, it's called primitive. So in dimension 2, we have two primitive delpetzes. It's P2 and P1 cross P1. In high dimension, we have examples, of course, varieties with rank 1. Delpetze varieties with rank 1, they are definitely primitive. Also, we have products like P1 cross P1 cross P1 and cross P2. And on the other hand, this is a classical example. We take P3 and blow up endpoints in general position n is less or equal than 7. Then we get, in this case, we get not Fano, but almost Fano. So we get almost delpetze. Easy to show almost delpetze. And if we take its anti-canonical model, then the result is imprimitive delpetze of degree 9 minus the number of the points. Okay. Another operation related to delpetzes is a Haplin section. Of course, this is a basic fact. Of course, you see, maybe first time in three-dimensional case, this analog of this was proved by Shakurov many years ago. Suppose we have delpetze variety of dimension at least 4, and take a general divisor from fundamental linear system. Actually, we can call it a Haplin section. Then this Y is delpetze variety, and the restriction map is isomorphism of lattices, and it preserves our form, and also preserves the element of the distinguished element A. And again, some extremal varieties with respect to this operation. We say that X is maximal if it cannot be realized as a Hepland section of high dimensional delpets. Strictly speaking, it's like it can be realized as a member of fundamental linear system of delpets, another delpets variety. Yeah, I recall that today we consider only non-conical ones. Okay, so examples are P3 and Grassmannian 2.5. They are maximal. For example, but the cubic and intersection of two quadrics are non-maximal. And two more definition, we say that delpets is unbounded type is there is infinite sequence of delpets such that one is Hepland section of another. Otherwise, we say that X is of bounded type. Okay. So first we stay we start with Imprimitive delpet surface. I was told that once we start with delpet variety, then we can set this, look at the Q factorization of this and run MMP. But MMP includes flops and blow down to the two smooth points. It turns out that this operation commute, and we can make flops first. But basically, this means that we can take another crystallization, and our MMP just composition of blowups. So for each primitive variety, we can picture like this, where X bar is primitive, and this is primitive almost delpets, and this is projection to canonical model, anti-canonical model. And of course, easy to see that the invariants, basic invariants, are changed as follows. So degree drops by k, and the rank increase by k. Okay, this is not so difficult, and now I'm going to talk about lattices and and classification of primitive delpets. So consider delpets variety, and in our lattice well-divided class group, we can consider elements of the following type. First, exceptional. This varieties, this elements, this just elements. I am not saying that it's effective divisors, which are has degree 1 and so some self-intersection -1. P1 type if it is degree 2 and self-intersection 0, and degree 3 if it is P2 type if it is degree 3 and self-intersection is 1. Basically, this one is analog of -1 curves on delpet surfaces, and these two are analog of pencil of conics. Okay, and it turns out, but this is just numerical, but it turns out that this is not only numerical. Again, by induction, we can show that The exceptional class, this is not exactly exceptional as usual says, but after some flops, it means that we can take suitable co-factorization such that this E is represented by exceptional divisor. Okay, and the same with P1 and P2 classes. If D is either P1 or P2 class, then there exists factorization such that its proper transform defines contraction to P1 or P2 respectively. Okay, so this means that the lattice is really reflects geometry, the same as in usual in a classical surface case. And a cone, of course, I recall that any weak Fano variety Fano variety is a Mori-Grimm space. So effective cone is effective and moving cone are finally generated. In the almost del Pezzo case, we can say even more. First, I should say that exceptional class generates extremal ray of effective cone, and P1 and P2 classes lie on the boundary of effective cone. And in suitable, for example, if we have suitable rank, then they generate extremal ray. So the fact says that effective cone is polyhedral. This is general fact, and is generated by extremal rays and finite number of extremal rays. And each extremal ray is generated either exceptional class or P1 class or P2 class. And similar for Mori cone, this is again or moving cone. This is polyhedral and generate a finite number of extremal ray rays. Each ray is generated by either P1 class, P2 class, or some big class which is a pullback of a birational map to the Pezzo variety of rank 1. The typical example is we can take P3 and blow up a point. Then one extremal ray is generated by pullback of Kaplan section of Kaplan. Okay, so now latest computations with lattices for primitive Fano gives us the following table. Just to explain, suppose we have primitive Fano variety of dimension n of rank 2. Then, since we have rank 2, we have only two small Q-factorizations. Of course, if it's already Q-factorial, then they are isomorphisms. And then we have on this second level, we have two Mori contractions. And then this is just computation that this doesn't depend on the dimension. this numerical computation shows that we have only following possibilities. We can have both p n minus 2 bundle on both sides in degree 1, 2, 3, 6, and we can have p n minus 2 bundle and quadratic bundle in degree 5 and two quadratic bundles in degree 1, 2, and 4. This is just numerical computation, but actually we cannot, we have no description. It's coming later. Okay. And primitive Pezzo varieties with of higher rank, it turns out that there are only few of them. And suppose we have primitive Pezzo variety of rank at least 3, then its rank exactly 3. And any equalization is Pn minus 2 bundle over P1 cross P1. Actually, we cannot get other Delpetzes because otherwise we have negative class on Delpetze. On the base, we have negative class and generates negative class of on the original variety. And it turns out that the degree can be 2, 4, and 6, and effective cone, this is the same as a moving cone in this case, looks as follows. In each case, is this size triangle, square, and 6 angle. And extreme arrays are P1 classes. This generated two projections on this P1. Okay. As a corollary, we have that the following inequality. I recall that in the surface case, we have equality for surfaces. In higher dimension, we have inequality like this. Why? Because it is valid for primitive ones, and if we produce in primitive, then blowing up of a point doesn't change left-hand side. Okay. Okay, and here is the classification. Not exactly classification, that is just some preliminary fact. Suppose we have primitive Pezzo variety with of rank at least 2 and take its utilization. First, if it has a structure of Pn minus 2 bundle over P2 or P1 cross P1, these are only possibilities, of course, then it is of bounded type. It means that the dimension is bounded. If it has a structure of quadratic bundle of P1 and degree is not 5, then it is unbounded type. And if it has structure of quadratic bundle over P1 and D is 5, then it's of bounded type, because from the table we know that Q-factorization has a structure of P n minus 2 bundle. The Pezzo varieties of unbounded type satisfy inequalities. D plus R is at most 6 and D is at most 5. Again, this follows from the above considerations. And finally, we have the following classification of Pezzo bundles. Pezzo bundle is a bundle, vector bundle, such that its projectivization is a Pezzo variety. Suppose we have maximal, such maximal bundle, so Pezzo variety is maximal corresponding. Then Chern classes, of course, we can think that first Chern class is just canonical bundle of the surface, and C2 is K, just number. Then, as a consequence, rank of this E is equal to K, and we have the following list. So this exactly this complete classification. For example, in this case, we see that this is just P2 cross P2. Okay, and the next, the similar thing we have for del Pezzo's bundles over P1 cross P1. And again, we have this classification. And the first case is again trivial. It's just product of P1 cross P1 cross P1. So we have we see that in each case this K is bounded. So bounded very effectively. Okay, and finally the same thing about quadratic bundles. It turns out that in this case, this is not it's not bounded except for degree 5. Degree 5. We have another structure, as I told that we have another structure. After flop, we have P n minus 2 bundle on the variety. And here we have three possibilities. This variety is realized as a divisor of type 2a minus kf on this projectivization. So this is not difficult, but very computational facts. So now I am going to consider example. This is classical one and maximal. I recall that we always have inequality like this. Since suppose we have equality, basically, except for one case which is not missing here, except for this one. This variety is obtained by blow-ups of P3 of points in general position. General position means that no four of these points lie on the plane, and there is no quadric which is singly in one point, and contain 6 others. This is for degree 1 only. Then just if we consider just blow up this blow up, then this x hat is almost del Pezzo, and its anti-canonical model has nodal singularities in almost all cases, and nodes comes from lines passing through pairs of points, and twisted cubic passing through 6 of these points. And corresponding del Pezzo varieties have some names, and in degree 6, this is one nodal hyperplane section of P1 cross P1. Degree 5, it's 3 nodal linear section of Grassmannian. Degree 4, this is 6 nodal intersection of 2 quadrics given by the following equation. In degree 3, this is 10 nodal Segre cubic, and in degree 2, this is 16 nodal quartic double solid, and it's ramified over a Kummer quartic surface. Actually, up to here we have varieties which are unique afterwards with below we have model. In degree 1, we have 28 nodal double Veronese core. Okay. This is example of computation of lattices. As in the surface case, we can take element of our lattice and suppose it satisfies the following inequalities. So it is orthogonal to the fundamental class and its length is -2. Then the set of such vectors form a root system. And here are two examples. If d plus r equals to 9, this is example from the previous slide, then we have types of the root system as follows. If d plus r equal to 8, then this is as follows. Okay. So this is very helpful in computation. Then we can compute everything. For example, exceptional classes, contractions to P1, to P2, and so on. And now the interesting point is geography. Geography means that with respect to two parameters, degree and rank. Okay, here is this another important lattice. Suppose we have a Pezzo variety of dimension D3 and take a general linear section, which is a surface, so the surface linear section, and consider restriction map. This is not isomorphism as in for local dimension, but it is isomorphism onto some orthogonal complement to some sublattice. So there is here we have a sublattice here which is negative definite, and rank of it equals to 10 minus d minus r, and the Dynkin type of this sublattice is a d or m. This m is as follows. It's at most 7 in each the previous two cases. Okay, and as a consequence of classification of primitive varieties, we know that the dimension is bounded. The dimension is bounded by this number in case A, and the cases dm in em are unbounded. Okay, and so we can write a picture. Picture is like this. Actually, we consider these lines and call them trains. And each train has some locomotive, and it starts from here, and we go from this direction. And this procedure is just a blow up of a point, and this is a blow up of a point, and taking anti-canonical model. successfully. So we have just the following picture of this. I recall that the first one corresponds to bounded type of varieties. And here is the classification according to the this Duncan type of lattice Xi. Of type A, if and only if this is either P3, Grassmannian, or this is pseudo-isomorphic to prioritization of vector bundle on some del Pezzo surface. This is another realization of this. Type D correspond to complete intersection of two quadrics of rank 1, or pseudo-isomorphic to blow up of quadratic bundle at points again. And type E correspond to del Pezzo varieties of rank 1 with of degree less or equal than 3, and their blow-ups. There are not so many possibilities in this case. You see that from the previous slide we don't have many possibilities. Okay, and finally, this is the last slide. The last slide, we have some very interesting duality in degree 1. I recall that the Pezzo variety of degree 1, we have this fundamental linear system gives us a map to Pn minus 1 with a unique base point. And this is a elliptic fibration. Elliptic fibration has a discriminant. And this rule gives duality between maximal del Pezzo varieties of degree 1 and smooth del Pezzo surfaces of degree n minus 1. And basically, this is given by projective duality. So discriminant is a dual variety to anti-canonical embedded del Pezzo surface. This is all. My time is over. Thank you very much.
Thank you. Are there any questions?
So I have two questions. I write them in the chat room.
Pardon?
So I have two questions, and I just type them in the chat room.
Chat. Just a minute. How to do?
So the first question is, why do we only care about log varieties of index n-1? Minus kx is equal to n-1 times an ample divisor instead of n-2, etc.
Basically, this is the easiest case. You see that if we look at Fano varieties, then Fano index is maximal number that divides anti-canonical class. Then it is, if it's maximal, then it's PP n. Next one is a quadric, and the next one are del Pezzo varieties. And basically, this is maybe easiest type of varieties. You know that, for example, MMP here is very, very simple. Next case is Mukai varieties. This seems to be more complicated. Again, we have classification of smooth ones according to Mukai, but still this is maybe in the next step.
And the second question was, does the construction of the anti-canonical model for the imprimitive varieties have any connections with Circus of links?
Yes, of course. For example, let me see. Just a minute here. Here we have typical Circus of link. If rank is 2, then we have typical Circus of link here.
If rank is 3, it's relation of Circus of links.
Pardon?
If rank is 3, it's relation of Circus.
Yes.
But if rank is
next stage is rank 3. Then it's this thing can be regarded as a relation between Circus of links.
And higher syzygies for R.
Yeah.
And higher kind of syzygies.
Yes.
Are there any other questions?
I have I guess a minor question. Is the ground field here C, and does it work on positive characteristic also, for example, n equals 3?
Other characteristic. Actually, you mean that positive characteristic?
Yeah. I guess.
Yes. Actually, we didn't consider it, but Fujita considered classification. There are some difficulties there, but at least I think that projective classification is almost done, even for singular ones. Actually, there are a lot of papers, Fujita's papers on this subject. Yes, but for other things, I am not completely sure that. Actually, I'm not. I don't know. We didn't consider. I think that many things can be done, but with care, of course. It's not. In dimension, at least in dimension 3, this is the same. But our point is that we consider maximal varieties. There are 3 operations, basic operation: a blow up of a point, taking hyperplane section, and taking special hyperplane section. And basically, this 3 operation covers the whole geography. Yes, but of course, in positive characteristic, there will be a problem. Okay, at the moment, I don't know.
Okay, thank you.
Any further questions? Well, in that case, let's thank Yuri again for the excellent talk.
Thank you.
And we'll, in a few minutes, Antonella Grassi will give the second talk of the morning session. So stick around. Thank you.